conference.
Yeah, I mean, I was just going to leave it in, but whatever. I remember to do it. All right. I'm going to cover two topics tonight, sort of like to make up what we missed. And then I'm thinking, speaking of the schedule, is we have one more lecture, and then the next lecture after next week would be the one where it's electrochem and exam 3, which I will never do to you to do the 2 exams. I'm sorry, the exam and then a lecture. So I was going to do one lecture of electrochem, but then I was almost thinking maybe we would just use next week to review, because that would be our last time together, right? There's only one more, right? Because there's 3 more basically.
Yeah.
I have to just look at my final. I don't think I have any in-depth electrochem questions. Like if I pull them, I don't think it'll make that big of a deal. So we'll see. I think we're all kind of hurting this year. And next semester, I get to teach in person, which, you know, my husband's like, oh, that stinks. And I'm like, actually, no, because I get to see people in person. I get to, like, you know, not be in the house yelling at my kids behind a screen so nobody knows I'm yelling at them.
We're all like, no, we want you home. Same. I stay at school, but when I used to stay home, I'd be like, no, I need to go somewhere else because this is, you know.
It's nice to just, be out. Ah, there we go. We got John.
So you're thinking next week would be a review?
Yeah, I'm going to look at I don't want to promise that. I'm going to look at the electrochem, but it's hard to really cover that. And I want to, you know, then you guys have the exam the day after. So I'll take a look at it. Maybe I'll do like electrochem light. And then we'll do, because we won't be able to do any review then.
Right.
If we don't. So yeah. And then that'll be our last time together. Wah, wah. All right. So let's talk about stuff that we need for the lab. I think that's our lab. Yeah, our lab has to do with this week.
Is that 305?
Yes.
Okay.
Yeah.
Awesome.
All right. Sophia and John, that's what I was doing. I was putting them in the attendance. Okay. All right. This is going to, I think, not be so bad. This is another K. So remember, we've had KEQ, we've had KA and KB. This is just another K. And this one's called KSP, and it stands for the solubility product. All right, so KSP. And just like any other K, it's exactly the same. It's basically products over reactants. So if we have something like calcium carbonate as a solid, right, and we want to see like, this is in equilibrium, right? So it's like you have a ionic compound that maybe isn't all that soluble. So let me look at my calcium carbonate. Yeah, so if you take a look at calcium carbonate, and I know maybe not all of you have this and didn't have me for Chem 1, but this is a chart, and this is in your lab book too. This goes over this, but a lot of ionic compounds are totally soluble. They have, you know, they're very soluble in water because water's polar and the cations and the anions can split apart. But there are ionic compounds that are not soluble, and you use this chart. So we're not going to need to really be able to use this chart. That's more Chem 1. But if you look, carbonates are mostly insoluble unless it's a group 1 or ammonium. And we're talking about calcium carbonate. So it falls under that less than soluble. So that's why we have this double-headed arrow, because it's not 100% soluble. So basically we write it like this. This is AQ, and then we have our carbonate CO3 2 minus, and again, AQ. So just to review, solid means it's a solid, right? It's physically a solid. And then AQ means it's dissolved. Now, sometimes we would just write this as CaCO3 as if it was still together, AQ, but in reality, it is actually broken up. And this hangs out with the water molecule. If you remember, water is polar and it has a slight positive charge and slight negative charge. So it can what's called solvate these ions and let them be okay with being out as ions. But since we're talking about the solubility, rather than write it as CaCO3 together, AQ, we're going to write it how it actually is, and that's in the cation and the anion. So the solubility product is the concentration of the products over the concentration of the reactants. But if you remember, solids don't have concentrations. It is a solid, it is a pure substance. A concentration means that it's an amount of the stuff we're talking about dissolved in some solvent, which we don't have. So the KSP is really easy because it's just going to be the product of the product. So it's going to be the concentration of calcium ion times the concentration of carbonate ion. And that's it, done, because there's nothing underneath because there is no concentration for calcium carbonate. Okay. So if we said this KSP is equal to, we can look this up in a textbook. These are values that can be easily looked up, and they're done by temperature. So this is at 25 degrees. They normally are like 25 degrees is considered room temp. So obviously the warmer a liquid is, or a solvent, a solvent is, the more solute can be dissolved in it. I always use the example of iced coffee, trying to get sugar going into iced coffee versus getting sugar to go into hot coffee. So again, if we had calcium carbonate and we looked up the KSP for calcium carbonate, we would find a number 8.7 times 10 to the negative 9th. And if we compare that with, let's just do lead chloride. So we have lead 2 chloride. This is a solid. And again, if we look at that chart, we're going to find that it's not all that soluble. So we would have a KSP for it, right? We would have a value. It's sort of like the same thing we talk about strong acids and weak acids. Like strong acids have a Ka, but because they almost 100% or basically 100% dissociate, the Ka doesn't really mean anything because it all dissociates. The same thing with ionic compounds that are highly soluble. We wouldn't really have a KSP so much because they mostly all dissolve, and it's just a large number. So anyway, I wanted to do this lead chloride because of this 1:2 ratio. So notice when I broke this apart, I got 1 lead 2 plus and 2 chloride 1 minuses. So make sure your stoichiometry is correct. So how this translates is this 2 becomes the coefficient, or excuse me, the exponent on your KSP. So my KSP for lead 2 chloride would be the concentration of lead 2 plus times the concentration of chloride squared. So that coefficient has to become the exponent. And we've seen this before where that becomes the exponent. And this is equal to, this KSP is equal to 1.6 times 10 to the negative 5, again, at 25 degrees Celsius. I'm not going to write the temperature for anything else, but just assume it's 25. So what does this tell us? This tells us that lead 2 chloride is much more soluble than calcium carbonate at 25 degrees, because remember, this is the number, this number represents the product of the product. So the fact that this is a magnitude of what, 4 larger, 1.6 to the negative 5 versus 8.7 to the negative 9, means that a lot more of the lead chloride actually dissociates and it gets solvated and dissolves in solution than calcium carbonate. So just like when we talked about Kas or Kbs, and the larger that value, the stronger the acid was, because it's always the product of the products over the product of the reactants. This too means the same thing. The bigger the number, the more soluble. All right. So let's do an example of how we would use this in a calculation setting. Anybody opposed to me erasing? All right, I'm going for it. So again, just keep in mind what Ks are. They're equilibrium concentration, or they're equilibrium expressions. They talk about where the equilibrium lies. Okay, so if we find the KSP for, what is this? This is lead 2 fluoride. So PbF2 is equal to 3.6 times 10 to the negative 8th at 25 degrees Celsius. So as soon as you're given a solubility problem, you want to write the dissolution reaction. So just like we wrote before, PbF2 and then double-headed arrow, Pb2 plus 2F minus. Okay, and then we're going to, what does this mean as far as this 3.6? So we can almost look at this as like an ice table in some respects. We could say like, okay, there's some amount of this, right? It doesn't have a concentration. So we have some of that. We have 0 of this, 0 of this. At some change, there's going to be some X of solid. Sorry, this should have a solid here, and this should have AQ. I might forget to put that in later. Some amount X dissolves. That means some amount X here. Now, this is where you have to be careful. We didn't run into a lot of this with the acids and bases, but for every one of these leads, we get 2 fluorides. So if one of these broke apart, we get 2 of these, right? So I always go back to my marker discussion. If one pack of markers has 1 lead and 2 fluorides, for every 1 pack of marker, you get 2 fluorides. So this becomes 2X. So again, this is minus X. And again, we don't care because we're not taking a concentration, but just to keep our ice tables correct, we would have this. But remember to write this KSP, we also use that to not only as the 2X, but we square the concentration. So when we go ahead and write this, it would be 3.6 times 10 to the negative 8th is equal to whatever the concentration of lead is, which we'll just call X, times the concentration of fluoride, which we call 2X, and this gets squared. So just don't forget that the coefficients act as our superscripts. So if we go ahead and solve this, we get 3.6 times 10 to the negative 8th is equal to X times 4X squared, or 4X cubed. I have these notes uploaded, and I just realized I changed from X to S. That doesn't, just notice that if you're looking at my notes, I just changed to S. It's the same thing. So if I solve for X, I'll leave it as X here. X is equal to 2.1 times 10 to the negative 3rd. And this is, again, molarities. We're in concentration. Anytime we use those square brackets, that means concentration in molarity. So what's equal to X? Well, this is equal to the concentration of our lead ion. And we take that and we do 2 times X, and that would be 4.2. So 4.2 times 10 to the negative 3 molar is the concentration of F, or fluoride, I should say. Okay, so that makes sense. Just number-wise, that makes sense. For every 1 lead, we would have double the amount of fluoride. So again, just don't forget to bring any coefficient down as far as your ice table X's, and that same coefficient is the superscript for that.
Can I ask a question?
Of course, go ahead.
I'm terrible with cubed algebra.
Yes.
Type of algebra. I actually don't know how to do.
Okay. I was going to say that before. I'll totally do that. So I know I hate this stuff. So what you look at it as is 2 of these, right? So it'd be 2X times 2X, because it's just this thing twice. So you can look at it. Huh? That
makes sense. It's the next line down.
Okay, right. So then I have X times 4X squared. So it's just 4 times 1. So we just get 4. And anytime you multiply coefficient, or not coefficients, what are they called? Coefficients. X's. Let's just call them X's. That you're adding their exponents. So this is like X times X, and you add 1 and 2. So that's where you get 3. So these get added. The exponents get added. So that's how you get to 3. So it's just basically the X, when you multiply it, it's just X plus the exponents. So that's how we wind up with that, because this is X to the first power and this is X to the second power. So the exponents get added. Does that make sense how we got to 4?
It does. How do you do the next step? The 4X.
Oh, okay. Oh, that's what you're talking about. Sorry. So that you have to put into your calculator. So what I would do, and there, I know there is a function, and some of the younger kids can tell you how to use it, but I would just take this 3.6, I would divide by 4. So let's do that together. So I have 3.6 second E negative 8, and I would just first divide by that 4. So I get 9 to the negative 9, right? So 9 times 10 to the negative 9 is equal to X cubed. X cubed, we have to uncube it. And there is a cubed root in here, but I just do this. I raise it to the 1/3. power. So when something is square root, it's raised to the 1/2. When something is cubed, it's raised to the 1/3. To the 4th, it would be raised to the 1/4. So I type it in as, I take my answer that I had, and then I use parentheses and just do 1 divided by 3. So that's what mine looks like there when I put it into my calculator. And then you should be able to hit enter and get, yeah, 208 or 2.1 times whatever to the -3.
Thank you.
Yeah, no problem. Yeah, like I said, I think there's something in there. I don't know how to find it though. I don't waste my time. Any root is just 1 over that raised to that. So that's how I remember that. Okay, so we're good on that one then. All right, so one thing I want to go back to real fast is just the idea of Q. And I'm trying to remember when we talked about Q. I know it was during equilibrium, but when did we talk about Q? And I don't mean QAnon.
Calorimetry, maybe? Was it back then? Like
no, like Q versus K. Like Q and K are related. Q is like you haven't hit equilibrium yet, and K is. So when Q, which is literally the same thing as K, but when Q equals K, you're at equilibrium, right? You've reached it. But if Q is less than K, that means it hasn't reached equilibrium and the reaction still needs to proceed to products. But if Q is greater than K, we've went too far and this needs to pull back and reaction goes to the left. So yeah, so as far as this, by the way, let me back up a second and explain KSP more. This is the solubility product, right? So it's how much can fit in a certain solvent. So if you had a bucket of water, how much, let's just go back to calcium carbonate that we had before. How much, what's the concentration, right? Moles of solute per liter of solution that can fit in this water, right? How many moles can fit in how many liters, right? This is your square brackets amount. And this is what your solubility product is telling you. Q is the same thing, but it's looking at it as a snapshot. So let's say I'm mixing up a bunch of stuff and I take the concentration. That concentration, because I don't know if I'm at equilibrium, is my Q. And if I take my Q and then I go compare it to what I know my KSP, but I forget where we talked about this. It was like the first time we talked about Q. It wasn't acids bases. It was, I'm sorry, K, when we talked about K before, but the same thing holds true. If I go and test my concentration and it's less than what the KSP value is, and remember KSP is just the product of the product. So there's nothing dividing it. So if my Q, my concentration at time wherever is less than KSP, that means more of my solid can dissolve up into solution already. If it's greater, that means that I went over. So I have a supersaturated solution, that stuff is going to precipitate out. So let's make sure we understand that word. After we pass the solubility limit at that temperature and we start adding more, or we cool this down, we're going to wind up with a precipitate forming, which is just the solid coming out of solution. So if I draw this on a little bit bigger scale, right, I have a certain amount of Ca2 plus and a certain amount of CO3 2 minus that can be floating around as ions. But then there is a limit, and the rest that goes in will be solid CaCO3 on the bottom as a solid. I liken this to like carrying a backpack. And like if you have a backpack and your strength for the day, your solubility is 5 books, right? You can carry 5 books down the hall and no books are going to fall out of your backpack. But if you have less than 5 books, you're unsaturated. So if I came and looked in your backpack and your Q was 4 books, that would mean that you could go further and carry another book. But if I looked in your backpack and you had 6 or 7 books, that means you're carrying too much. So how do we do that? We normally increase the temperature, make this supersaturated solution. The solution or the backpack is carrying more books than it would normally be able to carry because it's at a higher energy due to temperature. It's going to start falling out. Books are going to start falling out of your backpack, or calcium carbonate is going to start recombining and form a solid on the bottom because there's a certain limit. So That's what that means as far as Q goes. That's all I'm going to say about that. But just so we know what a precipitate means, like when you make rock candy, that's a supersaturated solution precipitation reaction, right? You heat up this water, you dump a bunch of sugar in, and then you put a stick that has some sugar rubbed on the outside, and it's a little bit spiky because it's a stick. And then as the solution cools, the sugar that's falling out of solution finds the wood stick, and it's all nice and to grab onto, and winds up making beautiful rock candy on there. So, although it never works as well in the lab. All right, so let's do a problem with this. The example I'm going to give you says find the KSP for a saturated. So again, saturated means holding as much as you can. Unsaturated is holding less than you can, and supersaturated is holding more. So when we deal with KSPs, we're always dealing with a saturated solution. That's what the KSP shows. So our problem is find KSP for a, I'm just going to put sat for saturated, and we're back to lead 2 chloride, right? If we find the chloride ion concentration to be equal to 0.0325 molar. Okay, so that's what a question would look like. Find KSP for a saturated lead chloride solution if you find your chloride ion concentration to be 0.0325. So first things first, we want to write this out so that we know what we're looking at. So we have PbCl2, that's a solid, and we're going to be in equilibrium with aqueous lead 2 chloride and 2 Cl minus, like that. So just like the last one, this is going to be X and this is going to be 2X. And my KSP, which is what we're trying to find, is going to be equal to X times 2X squared. And we know 2X, right? We know that chloride is already this. So what we're going to do is say, okay, if we know 2X is equal to this, what is X equal to? So be careful. The chloride concentration, which is equal to this 2X, right? So Cl minus concentration is equal to 0.0235, which we know is equal to 2X. So that means dividing by 2 would give us X, and that's what we need here. So we know chloride, and we know that half of the chloride concentration is the concentration of lead. So I hope that makes sense the way I said that. So we have KSP equaling, so I'm just going to put 0.5 times 0.0325. I'm just dividing the chloride concentration in half, and then I'm putting the chloride concentration and squaring it. And we wind up with KSP equal to 1.72 times 10 to the negative 5. And that's, oh, sorry, there's no unit for KSP. So we can say the lead concentration is whatever half of 325 is. The chloride concentration was this, and the KSP of lead 2 chloride in this solution is 172 to the negative 5. Okay, so we're going to use that number again? I feel like we're going to use that number. Oh, never mind. Maybe I changed. Well, the precipitate form. Okay. Are we okay on that? How we manipulated those numbers? Okay. All right. So I'm going to erase this. I thought this was on the same problem, but I think it's just a different problem using lead 2 chloride. So the question is, will a precipitate of lead 2 chloride form when 200.0 milliliters of a 3.78 times 10 to the negative 2 molar sodium chloride is mixed with a 100.0 milliliter solution of 2.45 times 10 to the negative 2 lead 2 nitrate. Okay. So we want to know, will a precipitate form when these things mix together? So let's think about what we're talking about. We have sodium chloride and we have lead nitrate. So again, if you didn't know and you looked at, okay, what's going to happen here? So first things first, we want to know if this forms when these two things are mixed together. So what do they mean? They mean if sodium chloride reacts with lead 2 nitrate. So this is a double replacement reaction. We're going to make sodium nitrate and we're going to make lead 2 chloride. Right. And I don't think, yeah, we don't need, I mean, we could just do that and we would be balanced, but I don't think we need to balance for this part. Well, what are we doing? So the rest of this problem said all nitrates here, all nitrates are soluble. Okay, if you had your solubility chart, you would know this is aqueous. If you remember back to Chem 1 where we had double replacements and we had to identify the solid, here's your solid, right? A double replacement didn't happen unless you made a solid, because this is aqueous and this is aqueous if we look them up. All nitrates are soluble, and I'm sure you know that sodium chloride is soluble. And this nitrate is soluble as well. So this is your solid. But we have a KSP. We have a certain amount of lead 2 chloride that will be soluble. So how much lead 2 chloride are we actually making here? And will we have a precipitate or not? So first things first is we have to figure out how much of this lead 2 chloride we're actually making. So we'll start by finding the chloride ion concentration. So how much of this are we actually going in with? So we said we had a 3.78 times 10 to the negative 2 molar sodium chloride. So what does that mean? So if we have 3.78 times 10 to the negative 2, and this is moles of sodium chloride per 1 liter of solution, but we don't have 1 liter, we have 200 milliliters or 0.2 liters, right? So this is just the way, and again, you can use a proportion to figure out moles of sodium chloride. So when you do this math, you get 7.56 times 10 to the negative 3 moles of chloride. Did I pick at the wrong line? Oh, no, I'm sorry. This is just moles of sodium chloride, excuse me. All right, so that's how many of that. But if we look at it, this is moles of sodium chloride, but this is also moles of sodium plus and chloride because they're 1-to-1, right? So this is all of it. This is, we had this concentration of sodium chloride, this much of that concentration solution, which means so many moles of sodium chloride and also moles of sodium and chloride. Okay, great. But what is the concentration of my chloride ion? Well, concentration is moles per liter. So we have 7.56 times 10 to the negative 3 moles of chloride over the entire solution. We're mixing 200 milliliters with 100 milliliters. So this is 0.3 liters. And when we do that, we wind up with a chloride concentration of 0.0252 molar chloride. Okay, so that's step 1. And I did not leave myself enough room. Okay, so that's step 1. Now, we also care about the lead. So we need to know how much lead we're going to have as well. So now we have how much chloride. Now we need to figure out how much lead. So we're going to do the same thing. We're going to say we started out with 2.45 times 10 to the negative 2. And this is moles of my lead chloride. Oh, sorry, lead nitrate.
Is the in the problem?
Yes.
Aren't they giving you the concentration, not the moles?
Yeah, this is concentration. Yep. So I have to break it down into moles first, and then figure out, because we're mixing 200 mils of one with 100 mils of the other. So we're like, for the sodium chloride, the chloride's going from 200 mils into 300 mils. So it needs to be adjusted by the volume. So
we find the number of moles per total volume.
Exactly. Yes. And in this case, yes, we could have just taken this, taken that, and then, basically, well, let me back up. this is how many moles are in 1 liter. So then we first have to take it out of that to find moles of just the thing and then divide by the new volume. So notice how we became, I was going to say less, hold on. We had this many, this molarity, and now we're a little bit less, right? So the sodium and the chloride is a 1-to-1. So we can say like 3.78 molar, right, to the -2 sodium chloride is pretty much is 3.78 to the -2 chloride ion. But we had to then divide that by the new volume. So find actually the moles and divide by that. And if you notice, it's a little bit less than what it was before, right? Because we're in 3 liters versus 1 liter. Does that make sense? Did I say that right? Okay. So we just found the number of moles of chloride. So we had a concentration per liter. We had to find out per 200 milliliters and then divide by the new volume, which is 300 milliliters, to get the molarity of just the chloride ion by itself. Now we're going to do the same thing with the lead. And we're going to, so we're just looking for lead, so we don't care about the other thing. So we're going to do the same thing. We are going to multiply this by 0.1 liters because it's 2.45 to the -2 molar lead nitrate per liter, but we only have 0.1 liter. So we're going to do that, come out of liters, and we're going to wind up with 2.45 times 10 to the -3. And I'm just going to write this as lead 2+. Now, what if I was looking for nitrate? What would I have done with this number? Anybody? Double it? Right, but we're not doing that. But I just want to bring that to your attention because for every 1 lead nitrate, I get the same number of moles of lead, but I would get twice as many nitrates. But we're not actually looking at nitrates. I just bring that up to say it. So here we have, this is moles of our lead 2. So we went out of concentration and we said how many moles are in that 100 milliliters. We have that. And then we're going to divide that by our 0.3 liters to get now a molarity. And that's 817 -3. So 8.17 times 10 to the -3. And that's molar lead 2+. So we now have, I know that was a lot of work just to get to that one section. So this is our concentration of chloride ions, and this is our concentration of lead ions. And going back to what KSP is, it's a measure of how much of one ion and how much of the other for a total concentration that can't exceed that KSP, or else you will have a precipitate. So we are now going to use those two concentrations in our KSP formula to figure out if we're over the KSP, AKA we have a precipitate, or we're under and we're unsaturated. So I'm just going to erase this part so I can continue up here. So I'll write in a different color so it makes a little more sense. Actually, I'm going to get rid of this one too. So what are we looking at? We're looking at the solubility of lead 2 chloride. So we have PbCl2, and again, just writing it out as the lead ion and 2 chloride ions. So again, this is going to be X, this is going to be 2X. And our KSP, if I write the whole thing out, it's the concentration of our lead ion times the concentration of our chloride ion squared. And our chloride ion is 2 times X, which actually, we don't even need this right now because we actually have the actual value of chloride, but that's what it would look like. This would be X and this would be 2X, just like our last example. But we actually have our concentrations now, so we don't even need to put in X's or anything. We know it. So we have a KSP equal to, I'm just going to grab my lead concentration of 8.17 times 10 to the -3 and multiply that by 0.0252, which is my chloride concentration, and make sure to square it. And when we figure this all out, we wind up with 519 -6. Okay, and what does that mean? So our KSP, if we look it up in a textbook, let me write this, I'll write this in a different color so we don't get lost here. We look up the KSP of lead chloride, and we find that the KSP at 25 degrees is 1.72 times 10 to the -5. Right? So that's what that means. It means that the combination or the product of the lead ion concentration and the chloride ion concentration can have a combined product of 1.72 to the -5. We are less than that. This is our Q. So Q is less than KSP, which means we haven't gotten enough lead and chloride concentration to be at that limit of how much it can hold, the backpack limit of how much, how many books, excuse me, that it can hold. So this means that we have no precipitation or no, what did I want to say? Precipitate. I can't even spell right now. No precipitate. How do we feel about that? Is that crazy town? Or is that okay? So keep in mind what KSP means, right? It's a measure of how much the concentration of these two ions from this solid can be allowed in solution at one time, because it's not a very soluble thing. So if you give me a certain number of moles of chloride coming from your sodium chloride and a certain number of moles of lead coming from this lead nitrate, you now have a measure of two of the ions concentrations. Put it into a KSP, find out where you're at and compare it to the actual KSP to figure out if you're at that limit yet. If you're below it, you're unsaturated. If you're above it, you have a precipitate. All right, talk to me. What are we feeling?
Do we ever need to look on the back of the periodic table at that solubility chart for these problems?
No.
Not really.
Not at all. No, that's Chem 1.
I forgot, apparently.
That was the good days when you could just say, that's a solid. Now you're like, now you have to calculate it. No, you don't have to.
Why isn't this on the chart, right? Everything.
Yes, focus on the chart. Okay, so that, just keep these calculations in mind. And again, just remember what you're calculating. Remember whether you're in moles or molarity, everything here should be in concentration. But like we just did, we had to come into moles to figure out the new concentration. And I can, I can imagine that that is confusing. And I hope that I'm explaining it well, because like this makes so much more sense to me now that I'm 20 years out from learning this or more. How many years has it been? Too many. But I remember this stuff not being fun to learn at the time. Like, I don't understand why I'm doing what I'm doing, but please ask me questions, because I'd rather explain it over and over again than to have you not understand it. So let's talk about solubility and common ion effect. So let's go back to our lead chloride, seems to be the example of the day, right? So we have this lead chloride that's got this minimal solubility of these ions, right? So remember back to Le Chatelier's principle that says, if we put a stress on an equilibrium, we can shift the equilibrium one way or the other. So if I go and add more chloride ion, I'm adding to this side of the equation. And in order to balance out, because there's only a certain amount that's allowed here, it's going to push back and revert back to product. If I put more product, I can then put more of this into solution. It's sort of like if you're at a party, you're at a club in the city, and there's a certain limit, right, of people that are allowed in there. So in order to let more people in, you're going to have to kick existing people back out. That's what's got to happen. So there is an upper limit of the amount of ions, depending on what you're talking about. We just looked at the other one, which was like 1.7 or whatever molarity that was allowed in. So why I'm talking about that is if I have a solution of lead chloride and it's just minding its own business, and I go ahead and add to that sodium chloride. Well, what you want to be looking for in this situation is common ion effect. So when this breaks apart, you are going to get sodium ion, who cares? But you're also going to get a chloride ion. So what that's doing now is it's messing with this established equilibrium, because this was at a point where there was the maximum amount of lead and chloride that was allowed in. And now all of a sudden you add sodium chloride. And what is that doing? It's adding chloride. Doesn't matter for the sodium, because the sodium is not affecting this, but the chloride is. So what this will do is it will then shift the equilibrium back towards product, reducing the amount that's in there. So, all right, so let's do an example. we're going to find barium and sulfate after so many grams of that or added to so many grams of that. Okay, so let me write this out. I'm going to take this down. That was just an example, but always keep that in mind when you're adding stuff. And this, I'm pretty sure that's what the lab we're doing this week is. Okay, so we want to find the concentration of barium and sulfate in the solution if 0.200 grams of barium nitrate. Remember, nitrates are always soluble. Anything nitrate is soluble. Or is added. 0.2 grams of barium nitrate are added. I don't know. I have R. That sounds weird. Are added to 400.0 milliliters of a saturated barium sulfate solution, whose KSP, this is for barium sulfate, is equal to 1.1 times 10 to the negative 10. Okay, so we have 200 milligrams, 0.2 grams of barium nitrate are added to 400 milliliters of an already saturated barium sulfate solution. So again, you should always see what's going on. So we have barium sulfate, and the fact that barium sulfate has a KSP means that you don't even have to check your chart. It's not going to be that soluble of a salt. That's why it has a KSP. So again, this is your solid, and these are your two AQs. And what are we doing? We're adding barium nitrate. So what is barium nitrate doing? Well, barium nitrate, being a supersoluble nitrate, breaks apart and gives you this. So nitrate doesn't matter because that's not affecting it, but the barium is. So we already had a solution that was at its maximum holding capability of barium and sulfate. And then we went and added more barium to it. So we have to figure out what's the new concentration of barium sulfate. And by the way, if we look at this KSP, let me just write it up here. You have Ba2 plus times the concentration of SO4 2 minus. This KSP doesn't care if it's barium or it's sulfate. It just says that the concentration of barium times the concentration of sulfate cannot exceed this 1.1 times 10 to the negative 10. So if we were already saturated before we added in this barium nitrate, that means the concentration of barium and the concentration of sulfate were at whatever limit, whatever numbers that when multiplied together equaled 1.1 times 10 to the negative 10. It was at that limit of carrying capacity. And we went and dumped in this. All right, so first things first, we need to look at the saturated solution of this. So I'm just going to pull this down here. If we know that 1.1 times 10 to the negative 10 is the product of the product, and for every one barium, we get one sulfate, we know that if we cut this in half, this equals the concentration of Ba and of SO4, right? So the product of these two things equals that. So if that's X and that's X, then we just cut that in half, or I should say, take the square root, take the square root, I should say. Yes. Let me write that as correct. So this is X, that's X, our KSP equals that times that. So this is equal to X squared. So if we just take that and take the square root, we are getting the individual concentrations. Let me know if that made sense. I kind of probably should have written that a little bit better. 1.0 times 10 to the negative 5 is both the concentration of the barium and the concentration of the sulfate. And you can prove it to yourself by doing 1 to the negative 5 times 1 to the negative 5 or 1 to the negative 5 squared. So that's the concentration of both the barium and the sulfate right now. And we're not touching the sulfate concentration, but we are going to mess with the barium concentration. Okay, so as far as the concentration of barium ion goes, what is it? Well, we know that it's 1.0 times 10 to the negative 5 moles of barium, moles of Ba2 plus per liter of solution. Again, we don't have a full liter, we have 400 milliliters. So this is 0.4 liters, which gives us a total of 4 times 10 to the negative 6 moles of Ba2 plus. Okay, now we know that's how many moles we have, right, in these 400 milliliters of this particular concentration of barium. But we're going and adding 200 grams of barium nitrate, right, to that 400 milliliters. So we need to find out how many moles that is. So we're going to take 0.200 grams BaNO3(2). And we're just going to do a simple mole calculation. How many moles is this? Well, we know 1 mole of barium nitrate, sorry if this is getting a little mushed together, I'm trying to save myself room, is equal to 261.35 grams of barium nitrate. So this is just your mole calculation. I added up 1 barium, 2 nitrates, and 6 oxygens, and that equals 261.35. And then if I were to stop right now and do 0.2 divided by 261, I would be in moles of barium nitrate. Now, obviously, you don't need to multiply and divide by 1, but I just want to make sure you understand where I'm getting this from. 1 mole of BaNO3(2), right? Because I'm getting out of moles of barium nitrate. I get 1 mole of barium ion. And the reason I'm stressing this is just because if for some reason it was 2 bariums or we were looking for nitrate or whatever, 1 mole of this would give 2 nitrates. But since we're just talking barium, I mean, obviously, again, we're not changing anything, but I just want you to see how the units get changed out there. So what does that mean? This means that we have 7.65 times 10 to the negative 5 moles of Ba2 plus. All right, so now we have this number of moles of barium and this number of moles of barium in one solution. So what is my concentration of barium together? Well, I am going to add these two together and then divide by the total volume. So I'm going to try to squish it over here. Hopefully you can still see. So I have 7.65 times 10 to the negative 5 plus 4.0 times 10 to the negative 6. So I'm just taking the amount of barium that was already here from my barium sulfate and the amount of barium we just added as barium nitrate. And I'm going to divide by the total volume of the solution. So we had, oh, it is just 400 milliliters. Never mind. That other one was a solid we put in solid 0.2 grams of barium nitrate. So we just divide that by 0.4 liters, right? Make sure you get this sum first. So in your calculator, you have to have parentheses around this addition, or else it will divide first. So do that, hit enter, and then divide by 0.4, or make sure you use parentheses. And this winds up as 2.01 times 10 to the negative 4th molar, and this is barium ion. So always label what you're doing so you know what you're talking about. Okay, so why do we care? Well, if you notice, we went from 1 times 10 to the negative 5th concentration of barium ion, and now we're at 2.01 to the negative 4th. So it's a 10-fold increase of barium ion. All right, so now we want to find, so that's my barium ion concentration. But what happens is, let me just back up a second and explain the equilibrium process. We were at our fill of barium and sulfate, with both of them having a concentration of 1 times 10 to the negative 5th. So if we just look at this equation, we had 1 times 10 to the negative 5th of this, 1 times 10 to the negative 5th molar concentration of that as well. But then we went and dumped in barium nitrate, which went and increased this. So this has got to now shift the equilibrium away. So who's going to suffer? I make it so anthropomorphized. Sulfate's going to go down because something's got to give in this exchange. And we just dumped in all this extra barium, and now it's going to affect the sulfate that's going in. All right, so I'm going to have to erase the top part. This is one good thing about being back next semester is, although I have to stand in front of that annoying lit up board, makes my eyes hurt. So we want to find our concentration of sulfate because that's what we wanted to find before. So just to refresh, this our KSP is the concentration of barium ion times the concentration of sulfate ion. So if we know the KSP and we divide the KSP by our barium concentration, this will equal our sulfate concentration, SO4 2-. And that's what we're looking for. Okay, so our KSP from before, so you're going to need this, is 1.1 to the negative 10, 1.1 times 10 to the negative 10 molar over the concentration of our barium ion, which is 2.01 to the negative 4 molar. We do the math and we wind up with a 5.5 times 10 to the negative 7 molar. And this is again our SO4 2- concentration. So let's take a look at what we did. We went from a 1.0 times 10 to the negative 5th concentration of both barium and sulfate. But by increasing barium from 1 to the negative 5th to 2 to the negative 4th, what had to give, the sulfate did. So the sulfate went from 1 to the negative 5th molar concentration to 5.5 to the negative 7. So again, using that analogy of the backpack, if you've got this backpack and inside your backpack, you have a bunch of square books and a bunch of circular books. Well, if you dump in more square books, you were already at your limit before, you're going to have to drop one of the circular books. And that's what happened. So our sulfate ion concentration went down significantly to account for the fact that we added a bunch more barium, and together that product of those two things can't be more than the 1.1 to the negative 5th. All right, how do we feel about that? All right, I've got one more example of this, of the common ion effect. And then we're going to move on to entropy.
Can I ask a question?
Yeah, go ahead.
I was with you when you found the original moles of the barium before 4 times 10 to the negative 6.
Yep.
And the next line where you have the 0.2 grams, I know you're doing stoichiometry, but you lost me there.
So this was added to the solution. So the solution was a barium sulfate solution that was saturated, right? It was just that, right? It was just this. This is what we were working with. So just imagine this in a beaker, right? So here's a beaker and there's some water in it, and we have a bunch of barium 2+ and sulfate 2- floating around happily, no precipitation, but it's right at that cusp, like one more little fleck of barium sulfate and it won't go in, it'll go to the bottom, right? So if you sprinkle some in, it'll just go right to the bottom. But what we did to this solution was we added 0.2 grams of barium nitrate. And what the barium nitrate gave us was 2 nitrates for every 1 barium nitrate, but it gave us barium. So it's adding to this amount here. So here I had to find out how many moles that was. So I said 2.2 grams of barium nitrate, and I just used the fact that 1 mole weighs this. So you just add up barium, 2 nitrogens, 6 oxygens. Now we're in moles of barium nitrate. And this last one was just to make sure everybody understood that for every 1 mole of barium nitrate, I get 1 mole of barium ion. Really, there was no need for that last part, but just to get out of moles of barium nitrate into moles of just barium ion.
So you don't have to account for the nitrate when you're doing that?
So it doesn't matter because the nitrate just swims around happily and doesn't have a solubility limit in water. So no, we only care about the thing that's going to affect the solubility, which is the barium. Because in our KSP, right, our KSP for barium sulfate depends on the barium concentration and the sulfate concentration. So if by me dumping in nitrate, it doesn't matter. It's not taking part of that. This is why it's called the common ion effect. So the fact that this barium nitrate shares a barium ion that is going to affect this equilibrium, we have to account for that, but we don't have to account for the nitrate. So we could look at the nitrate, but it's not going to do anything because it has nothing to do with our equation. What we do need is a number of moles of barium that we added. So then we just took our 2 moles of barium, the one that we had originally in our original solution and what we added. And then I just added them together and divided by the new volume, which was the same volume. It was only 0.4 liters. So now I have a new concentration of barium ion.
Got it.
Yep.
That makes, thank you.
Okay, no problem.
So it's really stoichiometry of doing 0.2 grams of barium to get the moles, and then you add the 2 moles together and
exactly
total volume. Okay.
Yeah. And you always have to keep track of am I in moles or am I in concentration? So that's where it gets tricky. So it's always, you know, do I have square brackets or not?
Okay, thanks.
You are welcome. All right, so the last problem, let's see. Okay, well, I'm gonna have to write this out. All right, so we are pouring in, slowly pouring in. Okay, so we have a beaker. So I'm just gonna write this. So beaker. Okay, in this beaker, we have a 0.14 molar calcium hydroxide and a 0.25 molar iron nitrate, iron 2 nitrate. Okay, now calcium hydroxide, so KSP for calcium hydroxide is equal to 8.0 times 10 to the negative 6. And the KSP for iron nitrate is equal to 1.6 times 10 to the negative 14. So right off the bat, we can look at these 2 KSPs, right? And remember what this means. You always have to remind yourself, it is the product of the products. So the fact that this is so much smaller means this is less soluble. That iron nitrate is less. Oh, did I write that? Hold on. I'm sorry. This is supposed to be hydroxide. I apologize. This is supposed to be hydroxide. Means that iron hydroxide is a ton less soluble than calcium hydroxide. Well, why do we care? I'm sorry, this is supposed to be calcium nitrate. I suck. I'm so sorry. This is why I'm messing myself up. This is calcium nitrate with iron nitrate. And then I gave you the KSPs or the solubilities of the hydroxides. So very soluble calcium nitrate, very soluble iron nitrate has a certain concentration. But I'm giving you the constant or the KSPs of the hydroxides of iron and calcium. Well, why? Because what we're going to do is we are going to pour in a 0.15 molar sodium hydroxide into this solution. So basically, what are we going to do? Well, we can write 2 equations. We have calcium nitrate, right? Or calcium nitrate plus sodium hydroxide. Well, what's that going to make? Well, that's going to make calcium hydroxide and sodium nitrate. And I'm not balancing this. I'm just doing my double replacement, right? So here's that calcium hydroxide. And the same thing's going to happen with the iron nitrate. So we have our iron 2 nitrate, and we're going to slowly pour in sodium hydroxide. Well, we're going to make iron hydroxide and again, sodium nitrate, very soluble. So just like a good double replacement, if you look on your solubility chart, calcium hydroxide and iron hydroxide are both solids. So if we were doing this, we would be like, oh my God, where's our product, right? Chem 1, I talked about that being your love connection. But the question is here is, given the concentration of calcium nitrate, which is a lot less than the calcium of iron nitrate, which one's going to precipitate out first? Is it going to reach the limit for iron first? Is it going to reach the limit for calcium? Now, I don't know. I don't even remember why I wrote this problem down because it's pretty straightforward. it's probably going to be the iron hydroxide because you have a higher concentration of this iron nitrate to begin with. You have more iron floating around. I don't care about the nitrate, but I have 0.25 molar iron 2+ floating around, and I only have 0.14 calcium floating around. So you picture those ions, right? So here's a bunch of iron floating around. Here's a bunch of calcium floating around. I'm going to start putting in basically hydroxide, right? Because sodium hydroxide, like we learned a couple of weeks ago, is a strong base. It's going to break up 100% and just be a source of hydroxide. So I'm going to see this hydroxide both here and here. And this is going to combine together, make my iron hydroxide. That's going to combine together, make my calcium. Well, what the problem is asking for is which one is going to come out of solution first? Which one's going to reach that limit? And again, spoiler alert, it is the iron hydroxide, but we have to actually prove that with math, okay? So let's go ahead and do this. All right, I'm going to give you a second if you need to write anything down because I'm going to have to erase a lot of that to be able to fit this. All right. So let me just get rid of this. Now we can all agree, hopefully, let me write this in a red marker, that if I have 0.14 molar calcium nitrate, I also have 0.14 molar calcium ion, right? Because for every 1 calcium nitrate, I get 1 calcium ion. So if I have 0.14 molar calcium nitrate, I have 0.14 molar calcium ion, which means the same thing for iron. Now, if I was talking about nitrate, I would double that, but I'm talking about the iron. So I would have 0.25 molar Fe2+. And finally, with sodium hydroxide, since all I care about is the hydroxide, I also have 0.15 molar hydroxide ion. So I'm just looking at my ions of interest. Again, I don't care about the sodium and I don't care about the nitrate. There's a whole lot of barking going on. What is going on out there? Okay, so we want to find the max amount of hydroxide for either one of these things. So let's just start with the calcium hydroxide. So if we have calcium hydroxide, your equation is going to look like this. Ca2+ plus 2OH minus. And my KSP, which I have at 8.0 times 10 to the negative 6, is equal to my calcium concentration, which, by the way, I know 0.14 molar. I'm just going to write this in parentheses, times, let me make sure I write this right. So my OH concentration. Let me just make sure I wrote the right thing. 8. Okay, right. And then my hydroxide I'm just going to write this as hydroxide concentration, and I need a little 2 there, right? And obviously it'd be 2x if I put that in, but I'm just saying hydroxide at this point. So I'm just going to solve. What am I saying here? I'm saying I know my KSP for calcium hydroxide is 8 to the negative 6. And I know that my calcium ion concentration is already 0.14 because I already had that told to me here. What is my max concentration of hydroxide that I can have? So mathematically, I take my 8 to the negative 6, divide it by 0.4, and then take the square root of that. So make sure you're doing it with me and you have the right answer. So I'm getting, and this is equal to my OH concentration, which is equal to 7.6 times 10 to the negative 3 molar OH concentration. Okay, so all I said is, I know I have that much calcium. What is the max hydroxide given that the KSP is that? So that means that at the moment where my hydroxide concentration is 7.6 to the negative 3, whatever that takes, because remember, I'm pouring in however much I need of this 0.15 molar sodium hydroxide. When I hit that concentration of OH, whatever that volume is, my calcium hydroxide is going to be at a limit and it's going to crash out. So let's find it for the iron hydroxide, same thing. So we have the same setup. We have iron 2+ plus 2OH minus. Same thing. My KSP for this is 1.6 times 10 to the negative 4, which is equal to my iron concentration, which I'm just going to write in as 0.25 times my OH concentration squared. And again, when I solve for this, my OH concentration, so I'm just going to take my 1.6 to the negative 4 divided by 0.25, square root of that, and I get 2.5 times 10 to the negative 7 molar OH concentration. So why? Why did I do this? I always want you to be thinking, why am I doing what I'm doing? Because just memorizing steps, sometimes it's not going to be in that certain order and you have to understand why you're doing it. What I did here and here is figure out, if I know how much calcium, what is the max hydroxide I can have in solution before I come out of solution. If I know my iron and I know my KSP for iron hydroxide, what is the max hydroxide given that iron concentration? And if you look at these two numbers, this again is the concentration of hydroxide. So this is a much smaller number than this. So this means that when I get to a concentration of hydroxide of 2.5 to the negative 7, that will be the limit to where, given the amount of iron I have and the amount of hydroxide I now just hit, I will hit my KSP limit and the iron hydroxide will precipitate out. But it isn't until I hit a concentration of 7.6 to the negative 3 that my calcium would crash out of solution. So that means that iron hydroxide would precipitate first, because the concentration of hydroxide needed with this amount of iron, the hydroxide needed to pull this out of solution and be too much for it to handle is a lot less than that one.
So it's like a limiting reagent.
Yeah, it sort of is actually. Yep, it is. It's that limit when you hit that. And yeah, it's the lesser amount. All right. Any questions on that? So let me just look at the quiz, and I think you should be, so you're going to have 2 quizzes this week. I apologize, but it should be pretty straightforward. Let me take a look here. Oh, one other thing I wanted to talk about was this and how it pertains to how you can use it with pH. Right? And we were just talking about hydroxide. That's what was getting me thinking about that. So remember that pH, this is just going to help you with one of the quiz questions. If I say to you, I have a KSP of some hydroxide, let's just call it XOH, right? Some hydroxide. And whether this is a 2 or a 3 or whatever, we'll just make it a 2 for now. If I have some KSP, we'll just call this 5 times 10 to the negative 3. I'm just totally making these numbers up. And I say to you, what concentration of X would be capable at a pH of, let's say, a pH equal to 8.5, right? So question mark, what is the concentration of X at a pH of that? So right off the bat, when you look at something like this, okay, they're giving me pH. Well, why are they giving me pH? What information can I garner from pH? Well, I know I can get the concentration of H+, but looking at this, there's no H+, but there is OH. So you have to remember that relationship. So if I go ahead and say, okay, pH is 8.5, but 14 minus 8.5 gives me POH, right? So that would be, what is that? 5.5. I hope I did that right. I should probably just use a calculator all the time because I can't do math. 14 minus
5.5.
Thank you. 5.5. Okay, so that's my POH. And if I take 10 to the negative 5.5, that gives me the OH concentration. Okay, so second 10 to the X. Make sure you know how to do this. This negative, this is the important negative that you cannot forget or you'll get the wrong number. You get 3.16 times 10 to the negative 6. Why do I care about OH concentration? Well, I have a KSP. This KSP is equal to the concentration of X times the concentration of OH, right? X plus or 2 plus OH squared. So I now have OH. So I can now stick OH in, making sure to square it. Make sure you have the right coefficients and stoichiometric ratios there. And then you can solve for the concentration of X from there. Does that make sense? There's a question like that on the quiz. So remember when a problem gives you something like pH, it's there for a reason. And if you ever get stuck on a problem, think about, okay, well, why are they giving me pH or whatever other thing that they're giving you that doesn't seem to fit? And think back, okay, what information can I get from that? Okay, well, if I know pH, then I know concentration of H plus, and oh, well, I have an OH, and how is that related? And there's a couple different ways you could have gone about doing this. You could have taken 10 to the negative 8.5 and divided the KW, the 1 times 10 to the negative 14th, by whatever that H plus was to get your OH out. You would have gotten to the same number. All right. So I just want to give you that. Everything else you should be fine with. There's a problem like that. There's a problem with a common ion, so you have to combine the ions. By the way, thiocyanate, you can look it up on the quiz. But thiocyanate is SCN minus. Okay, so silver thiocyanate is AgSCN. This is a polyatomic called thiocyanate. And silver is always a +1. And then you should be good. And it's multiple choice. All right. How are we doing? Doing good? This next part there's no math. Well, I shouldn't say there's no math, but there's not a lot of crazy math involved. Does anybody need a break? Need a bathroom break? All right, let's keep going. So we have talked about delta H, right? Entropy. Let's just make sure we remember that, right? So delta H or H, delta is the change in entropy, or enthalpy, excuse me. This is the heat of the reaction, right? If we have a negative delta H, this is an exothermic reaction. Heat is being let off. This is favorable, meaning that exothermic reactions tend to happen by themselves. Well, I shouldn't say that because a fire is exothermic. That doesn't happen by itself. But it continues to go after it starts because it kind of not self-starting, but it propagates itself. There's a better word for that. But if a reaction can give off energy and come down in energy, meaning it loses heat and is a exothermic reaction, a negative delta H, that's a favorable thing. And then we obviously have positive or endothermic reactions, and these are not favorable. They don't tend to want to happen by themselves. And remember what delta is. Delta is products minus reactants always. So when you have a negative delta H, that means your reactants were at a higher temperature or energy than your products. And an endo would be the reverse. In order for you to get a positive delta H, your products must have been at a higher energy. So if you remember these graphs, this was a long time ago, this would be an endothermic, right? This is energy or temperature, and this is time, right? So your reactants are here, and you went up in energy to your products. That's an endothermic. And this is endo. An exothermic would be there, where your reactants are at a higher energy than your products. You came down in energy. This is exo. This is more favorable to be at a lower energy state in the end. So that's enthalpy. Okay, delta H. All right, or just H. What we're going to talk about next is called entropy. delta S or S. Why they gave it an S, I don't know. Okay, S or delta S, this is entropy or the level of disorder, okay? Things are happier if they have an increase in entropy rather than a decrease. So I always use the example of, you know, your teenagers or your own bedroom. I know I'm definitely guilty of this. It's much easier to get it dirty and get stuff all over the place, clothes and shoes and whatever all over the place, and be less organized than to have it be organized. Like it took a lot more energy to get it organized and to keep it organized. So a positive delta S is an increase in disorder or randomness. Okay, and this is favorable. I'm just going to put favor over here, right? That's favorable to have an increase in randomness, like our universe tends towards disorder. A negative delta S is a decrease in disorder, and this is unfavorable or less favorable. And again, products minus reactants. So if our reactants are at a higher disorder than our products, sorry, let me say that again. Delta S equals products minus reactants. So in this case, we want our products to be more disordered than our reactants. So that's why the positive delta S is favorable versus the negative delta S. So the disorder of the products minus the disorder of the reactants. So where do we see this? Well, a delta S that's greater than 0, right? So a positive delta S. This is like ice melting, right? Ice going from a very ordered crystalline structure to a less ordered liquid structure, and then over to a vaporization, right? Going into the gas phase, that's less order as well. Although that's going up in energy or a positive delta H. But as far as entropy goes, ice melting, vaporization, again, like your room getting disordered, those are all increases in entropy. Another example is something like if we want to look at a chemical reaction, if we have 4C3H5N2O9, God, why did I pick that, right? Whatever this is, this giant molecule breaking down into 6 N2 gases plus 12 CO2 gases plus 10 gaseous waters plus 1 O2 gas. Okay, this whole thing going from liquid that doesn't have that much disorder, right? 4 moles of liquid to 6 plus 12 plus 10 plus 1 moles of gas. That's a huge increase in entropy, because a liquid to a gas is an increase in entropy or an increase in disorder. So this is a huge increase in entropy and very favorable reaction to go from liquid to a gas as well, increasing that. Okay, so when we talk about entropy, and we did this before for like Hess's law, we could say that the delta S for a reaction is equal to the sum of N times the delta H of the products minus the sum of N times the delta H of the reactant. So let me just remind you what that means. This is the number of moles. N is the number of moles, not noles, moles, right? As is that N. So just like we did Hess's law where we took, and this, by the way, this big E looking thing means sum, there's summation. So the sum of the delta H of the products minus the sum of the delta H of the reactants, just like Hess's law. So let's do a problem like this. And I would give you all these values that you needed. So if I had something like this, if I said calculate the delta S for N2 gas plus 2O2 gas yields N2O4 gas. Now, obviously, we decreased. We went from 3 moles of gas to 1 mole of gas. So we're going to have a decrease in entropy. And then you would look up stuff in your textbook, or I would give it to you. So if you want the delta S of the reaction, this would be the 1 mole of this. So 1 times the S of our N2O4 minus, and again, you need to put a parenthesis because this has to happen before you subtract it from there. So we have, sorry, this is a 1 mole of the entropy of N2O4 minus 1, the entropy of N2 plus 2, the entropy of O2, right? So there's 2 moles of O2, 1 mole of N2. We would get that entropy, subtract it from there, and we would get, and I won't bother you with the numbers, but you can look at the notes, is negative 297.3. And this would be in joules per mole Kelvin. That would be in your textbook. But as you can see, we have a negative delta S, which is less disorder. We decreased our randomness and we increased our order. We went from 3 moles of gas to 1. And again, I won't bore you with the numbers, but you can just plug them in. But just like we did Hess's law, you look at the product of the products minus the products of, or excuse me, not the product, the sum of the products minus the sum of the reactants. And this would be a unfavorable. Okay, so that is entropy or delta S. Now we have a thing called free energy, and it's given the symbol G. Okay, so free energy is basically the energy that's available to do work. Why they gave it G? I think, oh, it's Gibbs free energy. That's why it's G. So your G or delta G looks at a particular reaction and it tells you whether it's favorable or not. So a reaction that's favorable proceeds without outside assistance. Okay, so for example, water evaporates at 25 degrees Celsius by itself. We don't have to do anything, right? This is favorable. Right? You have a puddle of water outside, room temperature, it will eventually evaporate. It'll take a while. It'll definitely go faster if it was warmer, but this will be what's called a spontaneous reaction. Spontaneous does not mean it happens quickly. It just means it happens on its own. Another example is iron rusts, right? In the presence of O2 and H2O. You will rust iron. It's a slow process, but it is a favorable or spontaneous reaction. And then finally, sodium chloride dissolves in water, right? That does it by itself. Okay. Unfavorable, okay, would be water does not boil at 75 degrees, right? Water boiling at 75 degrees Celsius and 1 atmosphere of pressure. That's not going to happen by itself. That's unfavorable. Okay. Water does not freeze, right? At 15 degrees Celsius. It won't do it. It's not favorable. It's not a spontaneous reaction. You'll be sitting there for a long time waiting for that. But realize that something that's favorable in one direction is not going to be favorable in the reverse. So just like it was exothermic in one reaction, it's endothermic in reverse, or it's more disorder going forward, it's less disorder going back. So water evaporates at 25 degrees Celsius. It's not going to condense at 25 degrees Celsius after it evaporated. One's going to be favorable, one's going to be unfavorable. Okay, so what things are favorable? What circumstances are favorable? Well, a negative delta H and a positive delta S are what we call favorable, meaning spontaneous. Will happen without outside influence. And how we look at this in terms of free energy is if we have, so let's first talk about what delta G is. Delta G is calculated as delta H minus T delta S. Okay, so I'm sorry, hold on one second. Justin, you have your practice tonight at 6 o'clock. Yeah. Hold on a second. I have basketball problems. 6:30 to 7:30. Yep. I know it's a late one. Okay, sorry about that. So this is your reaction. Delta G equals delta H minus, by the way, this is temperature in Kelvin, delta S. So make sure you write that down, temperature in Kelvin. So, okay, so we pop in delta H's and we pop in delta S's and temperatures. What does that tell us? Well, when delta G is less than 0, you have a spontaneous reaction. So your reaction depends on, is it exothermic or is it endothermic? What's the temperature? And are you increasing or decreasing randomness? So if you do this calculation, the amount of entropy, the amount of enthalpy, and the temperature, I said those backwards. Sorry, enthalpy, entropy, and temperature. Do you get a delta G that's less than 0, meaning there's free energy, there's energy that can go out into the universe, which is favorable, or a delta G that's greater than 0 is non-spontaneous or unfavorable? Doesn't mean it won't go. It just means it needs outside, I think I spelled spontaneous, right? Outside help.
Can I ask a quick question?
Of course.
If you look up above where you just listed some favorable and unfavorable examples, is like water boiling at 75 degrees unfavorable just because all boiling is unfavorable, or because it doesn't really boil at 75 degrees?
So you can get water to boil at 75 degrees, but you have to lower the pressure. So it's basically saying like water, this will not happen. It's unfavorable at 75 and 1. It just means that no water will boil at that, and no water will freeze at 15 because of these certain circumstances. But you can get a water to evaporate at 25, and you can get iron to rust. I'm sorry, I don't think I answered your question. Ask me again.
I guess like if it said water boils at 100 degrees Celsius, would that be favorable?
Oh, yes. Yeah, for sure.
Because that's what it normally does. We didn't have to alter the state of anything.
Exactly. Right.
Okay.
Yeah.
Okay. Thanks.
So yeah, it's basically things that happen on their own without any outside interference. Like I could get water to boil at 75, but I'm going to have to, like I said, really lower the pressure on this.
Okay.
I can get water to freeze, but I'm really going to have to increase the pressure on that. So yeah, you have to do something to it in order to make that happen. But water will just evaporate on its own. Iron will just rust on its own, and sodium chloride will just dissolve. Yes.
Thank you.
You're welcome. Okay, so let's find out if the reaction is spontaneous or not. So let me give you some. So keep that delta G less than 0 in your mind. Okay. All right, so find delta G if delta H equals -218 kilojoules and delta S equals -765. Now watch your units, joules per Kelvin. Okay. I don't know why they do delta S's in joules and delta H's in kilojoules, but it seems to be the way to go. So just, it has to be in the same unit. So this is at 32 degrees Celsius. So remember, delta G equals delta H minus T delta S. Okay, so delta G equals, I'm just going to turn this into joules, or I'll keep that. What did I do here? I kept that in kilojoules. Okay, so -218 kilojoules minus, now here's my temperature. So I need 32 plus 273. It has to be in Kelvin because if you notice, this is in Kelvin. Oh, I didn't actually, sorry, I wrote it out as 273 plus 32. I probably could have did that in my head, but I'm going to leave it like that. And delta S, what did we say that was? A negative. Now I'm going to have to move this decimal point over. Yeah, so a negative 0.765 kilojoules per Kelvin. All right, so this would be in Kelvin. Kelvins would cancel out here, and I would get a delta G equal to positive 15.3 kilojoules. Unfavorable, not thermodynamically favored. Thermodynamically just means given this is thermochem, delta H's and stuff like that, not thermodynamically favorable. Now, could I make it happen? Sure. I could, we'll talk about this in the next section. Okay, so before we leave this, actually, what temperature does this work at? When would this become spontaneous? Now you could give me a reason, like when this happens, or a scenario, I should say, or we can actually figure it out. I have both. So just looking at the math, what can you say? Because we're not going to change the H and we're not going to change the S. So what would have to happen here in order to make delta G be negative? Anybody? No. What's the only variable I didn't talk about?
Well, you could raise the temperature.
Raise it. So that would make this more negative, and we multiply that negative by that negative. So this will always be positive. So would we want to increase the temperature or decrease the temperature?
Oh, you're right. Decrease.
Right. No, but it's hard. I bring this problem up specifically for that, because in a minute, we're going to talk about the temperature dependence, right? So if I go ahead and instead of, if I solve for temperature, right, I can say if delta G is equal to 0, which, or anything less than that, is equal to negative 218 minus T minus 0.765. I'm leaving out the units, right? I'm solving for T. That means T has to be equal to 285 Kelvin or less, right? Because we want this to be negative, and the only way for this to be negative is if the delta H dependency is higher. So we need this to stay negative because this negative and this negative are always going to be positive. So the larger we make this temperature, the larger we make the positive value of this side of the equation, and the less this negative can do. So we need to make this side as small as possible. So 285 or less on my temperature will make it so that the 218 or the negative, the exothermic enthalpy reigns supreme. So speaking of that, let's talk about favorable or non-favorable and our variables. So I'm going to leave this up here, and we're going to look at delta H and delta S, and then compare that to being fav or nah. I'll write it like that, fav or nah. All right. So we have scenarios. We could have negative, positive, positive, negative, 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 positive, positive. Okay. So hopefully this makes sense where I'm going with this. If I have a negative delta H and I have a positive delta S, right? So this would be negative, and I just put a positive there, but it's multiplied by this negative T. So my answer will always be negative, no matter how big or how small each one of these values are. Prove it to yourself, right? If I'm putting a negative value here and a positive there, which immediately is going to turn it negative, I'm going to have negative minus negative, negative, right? Or negative plus another negative plus another negative. So this is favorable, meaning it will happen regardless at any temperature, because you have what you need from enthalpy, you have exothermic, and you have an increase in entropy or disorder. So you're favorable at any temperature. So fav at all T's, regardless of what I put in here. I could put a tiny, tiny number. I could put a giant number, and it's always going to be a negative delta G. Okay. For the next one, I now am endothermic, which is not favorable, and I am becoming more ordered, which is not favorable. So here I have positive, right? I have a positive value, whatever. And then I put in a negative value, which is going to turn positive. There's no way, no temperature that I can put in, because you don't have negative Kelvin, that is going to make this delta G not positive. So this is unfavorable at all temperatures, does not matter. Any questions, stop me. Right? So regardless of what I put in, delta G will always be positive. Okay, so let's look at the next one. Now I have negatives. Okay, good on my delta H, but not good on my delta S. So here I have a negative value, but I'm putting in a negative value here, which is going to make this positive. So the only way for me to get this to be a favorable or a spontaneous reaction is if my delta H is the main driver, if this is enthalpy driven. And I want to take this temperature down super low, sort of like what we did in the last equation or the last problem, right? If this is negative, that's great. But if my delta S goes in negative, that makes it positive. So what I want to do is I want to make this T delta S component as small as possible by getting the temperature as low as possible. This way, the reaction will be enthalpy driven. So this is favorable at low T. Does everybody see that? How I'm doing that? And then finally, we have not favorable in our enthalpy, but favorable in our entropy. So again, this is going to be a positive value, and this is going to be a negative value. And this whole thing will be negative as long as our T delta S is going to be negative, because this is already positive. That delta H is not helping us here. But because our delta S is positive and we have this minus sign here, that makes this whole thing negative. So this is favorable at high temperatures this time, because as long as we keep that delta or that temperature component large, it'll make the T delta S component bigger than the delta H component, and so on and so forth. Okay. All right, so I have one little blurb next, and then we're done. Good, we made good time. All right, I'm gonna give you guys a second, just make sure you wrote that down. All right. All right, so finally, how can we calculate all of these things? So if we are looking for delta G, delta H minus T, delta S, right? So that's what we're looking for. How do we calculate this? Well, first and foremost, we can calculate our delta H a couple different ways that we've talked about over the semester, right? We have Hess's law, which we talked about, is adding different equations up, and remember flipping it and turning the exothermic to endothermic, or multiplying it by a factor or dividing it by a factor. We also could calculate our delta H through calorimetry, right? Our bomb calorimeter or something like that. Or we can look at the delta H of formation, which is like, okay, it took this much energy to form this nitrous oxide and this much to form this hydrocarbon or whatever. So that's how we find delta H. As far as calculating our delta S, we just do what we did before, and we look at the delta S of formation. So just like we did with the sum of the delta H's of the reactants minus, or the products, minus the sum of the delta S's of the reactants. So that's the only way we're going to find our entropy calculation. And then from there, we just calculate our delta G. And we can look at delta G's of formation. There are things like that, but we're just going to use this one up here. But we can find that from delta G of formation, and it's the same way. So I'll just write that out for you one more time. So the delta G of a reaction, if the information is accessible, you have the sum of the delta G's of formation of the products minus the sum, right? N means your number of moles, the delta G of formation of your reactants. Always the same thing there. Okay, so I just have another example there that I'll just let you guys look at, where you have iron oxide reacting with aluminum to produce iron and aluminum oxide. And I give you the values of that to find the delta G of the reaction. And you find out that iron oxide reacting with aluminum to form iron and aluminum oxide is favorable. It actually has a delta G equal to negative 838 kilojoules. But favorable, again, does not mean fast. So it doesn't mean iron oxide is plus aluminum is turning back to iron and aluminum oxide. The fact that this is negative just means it's favorable. Doesn't mean it happens fast. So let me just take a look at the quiz and make sure you guys are all set with that. Oh, where'd the quiz go? Okay. You guys have any questions for me?
If we review next week, are these our last quizzes?
It is.
Whoa.
Did I not publish this yet? No, it is available. Okay, I know. This is our last two. Let me just see. Yeah, so I ask you to calculate the delta H for a reaction given the delta H's of formation. I ask you to calculate the delta S, giving you the delta S's of formation. So just like we talked about here. And then calculating the delta G afterwards, given both of those. And then finally, whether it's spontaneous or not. Remember, spontaneous is negative delta G, non-spontaneous is positive delta G. And that's all she wrote. Any questions for me? Everybody's like, no, I just want to go home. Well, you are home. All right, well, then that's all I have for you guys. Yeah, so next week, I'm going to look over, I know some of you weren't here. I'm going to look over the electrochem, just make sure there's nothing I want to cover there. And we might just use next week as a review for exam 3 and the final. And then we have lab this week, and then we'll talk about what we're going to do with lab going forward. Make sure you get me your projects, and I'll remind you again of that on Wednesday. And Cindy comes to lab.
Yay.
When is the project due again?
I just need it by that that last date of lab.
Okay.
I had the thing up. Let's see. Yeah. So what? The 15th of December. Let me see. I should probably put that in there. It depends on when I have to get my grades in by. Yeah, I would say the 15th of December. Let's do that.
Yeah, I'm more like 6 inches.
And yeah. And I'll explain what we're going to do for the electrochem lab. I'm going to take a look at that. I might just give you that time to work on your presentation too. So you'll have that the 8th to work on that. All right, I'm going to stop